Welcome to the tutorial number 4. Today we concentrate less on theory and more on the tools that I use to model and solve uh, the optimization models. And in particular, we talk about the MPL modeling language. So MPL, it stands for Mathematical Programming Language, and it is the um, modeling language for mathematical problems. What is modeling language? So basically, it's the language that helps us to define the mathematical problems. So what we did before on the tutorials before, we always read the business case, then we defined model using the mathematical notation, and then we normally put this model into Excel and solved it. This is the good way to solve the problems, but Excel, it's not so extendable. It's very difficult to make changes to your model to make it larger. So it's not that easy to model mathematical problems in Excel. And therefore, instead of that, people use other solutions and in particular modeling languages and, for example, this MPL. MPL is developed by Maximal Software, so I hope you already visited the website. On the website, among different descriptions, you can often find the MPL manual. So on today's tutorial, we will look at this MPL language, but of course, we will not go through all the possible features, because that's not how you do it. Normally, you have mathematical concept, you don't know how to describe it in this language or in some other modeling language, and then you check the documentation. So here you also have the documentation. It's divided into 3 parts. So first 2 parts are related to modeling environment, to the software where we write down this language and what we do with it later. But parts 3, it's related to the syntax of the language. So it basically always shows you how this or that mathematical concept from the mathematical optimization model can be defined in the language. And we will today look at the models that we defined before using mathematical notation, and we will put them or define in this MPL language. So if we go to the tutorial, we have exercises. First exercise all the sub tasks. They ask you to model this or that formulation of the Dakota model using MPL. And then we will have a new business case and new problem. We will first read it, then we will build the or define the mathematical formulation, and then we'll put it into the MPL software. So I will now deactivate the webcam so we have more space, and we can start. So after you open the MPL software, I will divide screen into 2 parts. So after you open the MPL software, as in any program which works with files, you can create new file in the menu, and this is exactly where we write the model definition. Now, the first bullet point A in the exercise 1, it asks us to build an MPL model or to define an MPL model for the deterministic Dakota problem. So we formulated Dakota problem mathematically in the previous tutorial. It's here. Basic formulation. We will start with basic formulation and then go to the sum notation. And now we are asked to take this basic formulation and put it into the MPL. And then when we have it in MPL, we can press the button and find the solution. Previously, we used Excel for that. So basically, MPL language, it's organized, or all the problem definition, it's subdivided into separate sections. And every section, it represents some object of the model or some specific syntactical structure. So we start model definition with first section, which is called title. So every section starts with some keyword, and the keyword for title section is title. And then we can give to our model some title, which will be used later. It's not so valid for us, but later it will be used for information output, and it can be generally useful. So on the next line, we then start the contents of the section. It's not obligatory to put here some space on the line, but we do it to have to nicely format all the code so it's readable for us, for humans. And we will give a title to this model. So Dakota Model basic. You see here the underscore because contents of this title section, it should be one word. And here we have this one word. Even for us, for humans, it's multiple words. So there shouldn't be spaces. And then we end almost every line in MPL with the semicolon. Sometimes you can write some code on multiple lines, but still every expression should end with a semicolon. Next section that we will specify is it's related to the object from the model itself. It's the objective function. To start this section with objective function, we can have there are two types of objective function, maximization or minimization, and therefore we can use here different keywords. And for maximization objective function, it's the keyword max. For minimization, it would be min. Alternative variants would be, I think, maximize and minimize. So sometimes you have flexibility which exact keyword or in which exact way you specify sections, but we will not concentrate on it. We will have just some one version, which is max. If it were minimization, we would have here min. And so this is the maximization objective function. And then we write down pretty much here it looks the formulation of the objective function. In this case, for basic formulation, it looks almost exactly the same as we have it in mathematical formulation. So we write down -2, maximize. For maximization, we use star x1 minus 4x2 minus 4.2 x3 minus or plus 60 y1 plus 40 y2 plus 10 y3. This is the objective function. We end it with the semicolon. And so this is the objective function. It defines the coefficients of decision variables. And also from this objective function, MPL language understands what exact decision variables are there in the model. Of course, to know or to use the MPL language, you should understand the model formulations in mathematical notation. Therefore, if you still don't have intuitive understanding of this right part of my screen, I suggest you to go back to one tutorial back, because otherwise it will not make so much sense. So we defined the objective function. Next section, it will be exactly the same as is in mathematical formulation. It will be subject to, which define constraints, and here line by line we will define this constraint. Every constraint has quite similar syntax to objective function, except that we have also here right hand side. So I write down 8 y1 plus 6 y2 plus 1 y3. And then less or equal, I write basically less and equal x1 and then semicolon. Another two material constraints, I would write them in the similar manner, but I can just copy. them from the solution, and here spaces, so they don't really matter. So I can put any amount of spaces that I want, and coefficients and so on. And I will align my solution, neatly align it, so I have a nice overview. I can also align it in any ways that I want. Now, next constraints, these are demand constraints. Such constraints which have the only one variable on the left-hand side, they are often called the bounds. So for example, here it says that variable, decision variable y1, it cannot be higher than 160. So this is the upper bound because it limits from above. This is the upper bound of the decision variable y1. We could write it down here, y1 less or equal to 160, but there is a specific section for the bounds in MPL, and it's called bounds. So we write down here 160, upper bound for y1, then for y2 is 115, and y3 is 209. So this bounds, it has a meaning for humans. If you go deeper into this domain of optimization, for many people, they use this terminology bounds for such constraints. It's also important for solution methods, which for us is not that important. And it's also sometimes changes the efficiency of the software when we solve problem if we correctly define the bounds, if we specify that bounds are bounds. But all this is not that important for us. So if you would write this bounds as a constraint, not a big deal. Then we have here non-negativity constraints. But in the same way as for Excel solver, the same as here, all the decision variables, they are by default assumed to be continuous non-negative decision variables. So this line of non-negativity constraints, it's something what is assumed, and we don't need to write it down explicitly, even so we could. So we could write down x1, again, it's a bound. You see, it's non-negativity constraints. They are basically lower bounds because they say that x1, it cannot be lower than 0. So we could write it down more equal to 0, but it makes not so much sense. And then we can, as far as I remember, it's optional, but we can specify the end of model definition with end syntax. And that's how we define this model. Now, first of all, we can save it. So we can go to the file, save as, and then let's say that we save it to desktop. We call it Dakota Model Basic. So we saved it, and then on our desktop we will have the file. It has an extension MPL, but it is basically, if we open it with some notepad or some software that reads text files, like I have Sublime Text, you will see that it's a simple text file. So this model definition, it's nothing else than text file, and I can even edit it here in the text editor, but we defined it in the MPL itself because we have here some additional features. Now, so we define this model, what we can do with it. First of all, you see here the small icon, which is like some tick mark. And if you press it, it will check the syntax of the model. And you see here the syntax of the Dakota model, basic MPL, is correct. Now let's try, for example, if I would forget here, if I would put space between Dakota model and basic and check it, I would have some error. So it shows the exact line line contents, and it says that a minor mistake was found in line 2. It's really line 2. And here it expects something. So sometimes these errors, they're a little bit like not that clear what exactly error is, but at least you always know the line. And as we define the model, and it's correct, we can press this icon, which is the mountain with the arrow on the top. So it means we want to find the optimal best solution. So I press it. And here I get the status window, which says optimal solution found. If this problem were infeasible, it would be here written infeasible or unbounded, unbounded, and so on. Then we have some statistics about the file itself, how many lines it has, 17. So it's the lines in the definition. Then statistics about the model. So this model, it has 6 variables, 3 constraints, and we see that these are the 3 constraints. Bounds are not included. Non-zeros, so it's the number of non-zero coefficients in the matrix A, and matrix A is the matrix which is taken from this standard definition of the model in matrix notation, which we had, I think, on the previous tutorial, and number of integer decision variables, because so it's 0 because in this model we have no integer variables. And then you see here phase 1, it's step in the simplex algorithm, which is not valid for our course, and then or not important, we don't look at it. And then the total is the objective function. So you see that the objective function is 4219, and this is the, in other ways, it's the maximum value of the objective function, and objective function is the profit. So this is the profit. Also, you can press here OK, then you will close this window, or you can press View. When we go to View, we get here more detailed information about the solution. So we have some log information from the solver. So it's just how long it took to solve this problem. Of course, it's 0 seconds because this problem is very simple. Which solver was used, and the so about solver I will tell in a second. Then again, the objective value, in our case it's profit. And then here we see the decision variables. And for every decision variable, so they're listed here, we have activity. Activity is the value of the decision variable in the optimal solution. And then we have here reduced cost. Reduced cost is used for analysis of the solution. So-called sensitivity analysis, it's not important for us. And then we have information about constraints. It's also less important for us. Now let's go to the solver. So what it means that you have see here simplex solver, and some information is provided. So what's actually happening when we press the button solve? First of all, this model in MPL notation, it's parsed. So this software, it looks at this model and it parses it into the general model formulation. General formulation, so we had it in the previous tutorial. It's this formulation with vectors and matrices. And then these vectors and matrices, they are stored in memory and they are passed to another software, which you don't even see here. It's so-called solver. So solver is the software that doesn't have a user interface, and it receives objects from here, from the results of parsing this model, and provides you the solution. And when you go to the menu run, you see here solve simplex 300. So it will be equivalent, if I press this button, equivalent to this icon, if I press this icon. But I can, in this run menu and solve submenu, I can choose here other solvers. So these is software that can be really used to solve this problem. And now we use simplex, but there are some other. This is all information is not important for our course, but for your general understanding. And when you use some other modeling languages, which also have syntax, which have modeling environment, like here we have this window, but it could be something else, they all work quite similar. They parse what you write in them. They uh, build these general objects, which are matrix A, vector X, and so on, and then they pass them to some of this software to which they're connected. And all these solvers, they were installed when you installed MPL. Now, we will do one more thing for the MPL deterministic model. We'll now formulate it using not this basic formulation, but using the sum notation. So using this notation, and we will look how this will work. So I can basically close this file, and I will create the new model. And now in MPL, we will try to reproduce the formulation of the model using sum notation. In the same way we started with the model definition with the title section, and right here, let's call this model again the Dakota model, but then sum notation. So Dakota model, sum notation, semicolon, and then which section we define now. So first we define the sets that are present in the model. Here we have two sets, set of products and set of resources. We define sets with the keyword index, because these sets are basically used for indices. Now, the first set will be product. So I could, of course, use this letter, but I can use a normal word, it's product, and by convention, I will use the all capitals to define sets. So it will be product, but we could write it down in any ways, not capital, but sentence, case, and so on. And then we specify which members this set has, because we need to provide this data. Here we assume that, so in this formulation, we know that look at the model explanation and you will know what are the elements of the set of products. But here we need to explicitly specify it. So we use not the equal sign, but we use a colon and equal sign. And this means the assignment. Because if it were equal, it would be equal as in the constraints or as in the objective function. We will look later. But here we define the values which are in the product set. And then we round the elements of this set. We could write down here the numbers, but we can use the words to define the set. So we start with the bracket, and then we write down that first element in the product is desk, right? Then table, and then chair. Then we close the bracket and semicolon. So here we could use numbers, but why should we use them if we can explicitly in more clear way define what are products? Next are resources. So again, resources, and we defined it. And we have three resources. It's lumber, finishing, and carpet. These are all sets in the index section. So now we go to the next section. And we see that here we have the parameters in this problem. So x and y, these are decision variables, but here are parameters, which are c, q, w, and d. So cost, selling price, cost of resource, selling price, requirements, and demand. And all these parameters, they have some exact values. So we defined which parameters we have and their values in the data section. And here we start with the selling price. So we will not, here it's called Q, the letter is used. We will just use the word price, even so we could use a Q. And then we see that this price, it has the index. And index, it is the product. So price is defined for every product. And we write down these indices for parameter price in the square brackets. So I open the bracket, and then I write down here for what this price is defined, which index. And J, it is the product. We defined the index of products or the set of products as products, so I can simply copy it here. So what it says here is simply that we have a price for every product, specifically desk, table, and chair. Again, we use colon and equal sign. And then as here we define the set of products here, we open the bracket and we define the selling price of products. Selling price of of the desk, it was according to the problem 60. Of the table, it was 40, and of the chair, it was 10. You can find these values in model description. So it's in assignment, there is, for Dakota model, there was a table which provided us exact parameters, and the price was 60, 40, 10. And next, and of course we use semicolon. Next will be cost, and the cost is defined, you see here, of one item of resource I. So here we will use resources now, because it's defined for resources. We have 3 resources of the price 2, 4, 5.2. And now next will be demand. I will write it down after the price. Demand, it's also for the product. That's why I write it after the product. And the demand for desk, it was 160. It's a deterministic model, so we don't have scenarios. One scenario, so to say, it's 115 and 290. Now, so this all were, if you imagine it as a vector or as an array, these all are one-dimensional arrays of vectors, meaning that every parameter here, it has only one index. But now comes something a little bit different. So if we look at the parameter W, which means the requirement of resource, it has 2 indices. So it's the requirement of resource J to produce one item of product I, right? So here you can imagine it. So this you can imagine as a row in Excel table. It's one-dimensional parameters. But here it's like a table where you will have basically the rows for index J, so for resources, and columns for product I, so for product. Now let's define it in MPL. So we will also write it down in normal word, which will be consumption. And then it has 2 indices. So first index will be resources. I can copy it. And second index, it's product. the same as here, J resource, product I. Again, we defined it. And now, how do we write it down? So I open the bracket, and you can imagine that now I write down the first row. And as I said, rows are related for resources, columns for products. So first row, it's the resource lumber. If I go back to the table from exercise 2 of the tutorial 3, I see here in this table, it's also represented in the same way. In every row, which is related to a resource, we have multiple columns for production requirements for resource consumption, and every column is then related to the product. So the first row for lumber, it has coefficients 8, 6, and 1. And again, the meaning of it is, so resources, its first resource is lumber. So, and then products, so 8, it's related to desk, 6 to table, 1 to chair. The next row, and there are different ways how these multidimensional parameters can be specified. So we can simply put comma here and then write the next row without any spaces and so on, because MPL, it knows the number of resources and number of products. So it will know, okay, now I start with resource 1, which is lumber, and check, read these values for all the products. So it's 8 for product 1, 6 for product table, 1 for product chair. All right, now I read all the products, I go to the next resource, and next resource, it's finishing, and in our formulation, it's also finishing. So I specified it as 4 from this table, 2, and 1.5. And the next would be for carpentry, it's 2, 1.5, 0.5. Then I close the bracket, and I'm done, and put the semicolon. To make it more readable, I can add the lines here. So I can add the lines and then align it in a better way. And it will be interpreted exactly in the same way, but now it's more readable for humans. And then these commas, they are not necessary. So I also delete the commas that I see that it's the end of the imaginary row in the table. Now it's with this multi-dimensional or two-dimensional parameters, it's also important to understand. So the first index, when you imagine it, it's related to the rows, and the second index is related to the columns. If in this definition I would change the positions of them, then it would mean that every row in this data, it's related now to products and column to resources. And then my values, they would be not correct, not as they are defined in this table. So I would, if I want to do something like this, due to some reason, I would have to modify these values so they are correct. And another thing is that also in which order we provide here the sets. Because if I would change the lumber and finishing, change their positions, it would also mean that this data is wrong, because then the first row would be related to finishing. And for finishing, this consumption or requirements, they are not 8, 6, 1, they are 4, 2, 1.5. So you should just understand what are rows, what are columns for these indices, in which way they are provided. And now, so we defined the W, requirements of resource or consumption of resource. And this all data that we have. Now, before in the basic formulation, we provided the objective function, and from objective function, it was clear which decision variables are present in our model. Here we will do something else. We will explicitly define what are decision variables in our model. And for that, we can use the section which starts with the keyword variables. And now we have two decision variables, xy and xi and yj. So it's xi, it's purchased quantity of resource I, and yj is manufactured quantity of product j. So we will not use these letters, we will use normal words. So yj it's yj it's manufactured or produced quantity, so it's production. And then we see that it has index j, and index j is the related to product. So the same with the data, we defined how this decision variable it's indexed, and it's indexed of the product. And then you intuitively, when you read it, you see it's the production of products. It's not production of resources. And then again, we provide the purchase quantity of the resource. So we write down purchase and then resources. We don't have any other decision variables. We would have some decision variables that doesn't have index, like fixed cost. We could write it simply down fixed cost, due to some reason. We would have it, and then it's the decision variable without indices. And now when we define this, we go to the objective function. So for objective function, we have decision variables, which we already defined, and we have coefficients, because in the objective function, coefficients are ci, and ci it cost of the resources, and qj, this is the cost, this is the selling price of product. All right. And objective function in this mathematical notation, of course, it consists of two parts. First, it's the cost. So this first ci xi, the sum of them, is the cost of the resources, and next part is the income which we get from selling our product. And now, of course, so this cost, it should have a negative sign because it lowers our profit. I just fix the solutions. Yeah, so it's with the negative cost is with the negative sign. Now let's start to formulate the objective function. It's still maximization. And now we start with the costs. So there we sign minus, so it's minus. And then we go to the sum notation. So for sum notation, we use the keyword sum. And then we open the bracket and we specified the sum over which set do we want to find. Here we see it for every I in the set K. K is the set of resources. And for resources, we have the set in indexes section. So I can simply, I simply copy here resources and then put the column. And it means find the sum over every resource. And then after the colon, I specify what will be the elements of the sum, and it is the multiplication of the cost and the purchase amount of resource. So I can write down here cost multiplied by purchase, and then close the bracket. I don't need here to write down something like cost resources and so on, because MPL will understand if it's the sum of resources and costs and purchase defined for resources, then it will correctly find the sum. Now we go to the next part. It's the income from selling the product. And again, it's the sum, but not over resources as was for the costs. It's for products, sum over products, J in the set of products, and here we multiply the selling price of products with the production of every product. We close the bracket, put the semicolon. So this is our objective function, which is the MPL formulation for this mathematical construction. Now we can here use some, I would say, syntaxical sugar to make this more readable. So when I explained it, I said that this is the total costs. These are the sales, total sales. So why don't we somehow explicitly for humans specify that this is cost and this is the sales, so that they don't need to analyze this. Okay, we multiply cost with purchase, that's why it's total cost. And for that we can use macros. So macros, we can add the section with macros. Macros, it's some, let's say, formula definitions or its expressions. It's easier to show than to explain. So I will define first macros, which I will call total revenue. And then I use the equal sign to define what it is. And total revenue, it's basically this. It's the total sales, total revenue of the product. So I can copy the sum over products for price and production multiplied by production. I can copy it here. So I define the total revenues, the formula to calculate total revenues as a macro. The same I can do for total cost. So it's, as you might guess, it's this, which we already defined in the objective function. So total cost, I don't put here minus because minus we use when we calculate the profit, right? And now why did I do this macros? Because now I can use it in objective function. All the thing I can substitute with total cost. And this second part I substitute with total revenue. And now when we read the what we want to maximize, we can just look, okay, we maximize the total revenue minus total costs, which is the total profit. I could even specify here, so write down something like total profit and write these both things, yes? And then if I would have macros for total profit, I could, instead of these two things, write here total profit. But I will not go to this level of abstraction. We had now the, this is the objective function. Now let's go to the constraints. So subject to. And here we have in this problem constraints, which is the second line. And so in some notation or in this shorter notation, this looks as a one constraint, but if we expand it, basically we know that the second line, it's many constraints, because it says this constraint should be like that for every resource I in the set of resources. So the number of this constraint, resource constraint, is equal to the number of resources. And then this first line, as we discussed before, for the basic notation, this is not the constraint, it's a so-called bound. So let's then start, instead of constraints, let's go to the bounds, and define there this demand bound, demand constraint. So it looks as that it's defined, or it should be like that for every product where the production amount of the product is less than demand. So how do we define the bounds? The easiest version is first we can write down production. So I added the section for bounds. So production. And then I don't need to write here index. I can simply write down less or equal than demand. And MPL will understand that since demand is defined for products, production is defined for products, then it means that, and I don't provide any other additional information, this like this should be for all the production amounts of every product. What additionally I can do, I can give a name for this bound. So before the bound, I can write down its name, and I will name it, let's say, demand. And then I put then I put colon. And now this bound, it has also some description demand, and it's its name. That's how I define the bound. Yes, now let's go to the constraints. So I can also, in this same way, provide the name of the constraint, and here I even should do it. So I will name this constraint as resource constraint because it's for resources. And now we see here it should be like that for all i's, so for all the resources. And this expression for all the resources I write down after the constraint name. So I open the square bracket and I write down here for all the resources, so for resources. And this is a syntax similar to like index, because this resource constraint will be related to every resource for resource lumber, finishing, and carpentry. So it's something like index for constraints. Now I put the column, and we start with the left-hand side. So here it's the sum of over, so for j in n is the set of products, and then we have some elements in this sum. So the sum over all products, we had this construct here, so we can sum over products for which elements? wij, it's consumption, yj, it's production of products. When I write down again these elements, their multiplication as an element, I don't need to specify any kinds of indexes because MPL will understand. Okay, we have sum for products and it's defined for every resource. It will understand what put instead of this I and j. So it's consumption multiplied by production. Now, right hand side, the same as in the basic version, we could put less or equal. And then here also, as you might guess, this should be less than xi, which is the purchase of every resource. So we can write down purchase. And we also don't need to specify here index because MPL knows that resource constraint is specified for every resource. So it will be the purchase for the relevant resource. And then semicolon. And this is basically is this model. And now I can put here end, the optional syntax. And now, so you see here that with this formulation, if you would like to add one more, let's say, chair, or one more product, or one more resource, it will be quite easy. You would just expand so set of resources, for example, for resource, then costs of resources, which is in the data section. But as long as your structure of your problem doesn't change strategically, these parts, they would be always the same. So you would only change the indexes and data. And it's quite handy if you want to play with your model, or if you want to add some products, delete them. And it's like that for any problem which you define in some notation. And if we would look at the basic notation which we use there, we would have, which we used before, we would have to edit all the parts of the model. And now we can check the syntax. Let's see if it's correct. Oh, so it asked me to save it before. No, it doesn't. The syntax of Untitled is correct. All right, let's save it so it doesn't. I will save it on the desktop as a sum, Dakota Model, sum notation, save. again. Yeah, so the syntax is correct. And now when we solve this model, of course, the solution should be the same if we entered all the data correctly and if we defined it correctly. Now we see it without syntactical errors, but we didn't miss anything. And we see that optimal solution is the same as in the basic solution, the same as what we had in Excel. Now we go to view. So to view the solution, exactly what we are suggested to do. And here we have neatly total revenue and total cost. So the values of the macroses, not only the value of objective function. And then we see here also for product, it's not some x1, x2, x3, and so on. It's the nice, understandable words and activity. It's the, here we know it's the production of product. So it's amount of production. Um, and here we have the purchase amount. So it's the amount to purchase for every resource. Uh, Additional information that we get about this model, it's you see this icon, which whatever it looks like, the rightmost one. If you press it, you will get the information about model definition. And the model definition, it's shows you all the objects that are present in your model. And this is the result of model parsing. So when you define the model in, so to say, textual form, sometimes it's useful to look at the model definition where you can see which indices you have, which data, which variables, which macros, and which constraints you have. And then you, for data, for example, you can check the values. So maybe your model definition in textual form, it looks very complicated because for big models, it can be very complicated. But then I'm interested, okay, did I define the price of products correct? And I can press it 2 times and then I see exactly what are the values. All right. So this is often rather handy. And it took us a while, but now we know the basic syntax and the most important one for MPL language, and we can define very many more or less simple models in MPL. And we can go to the next exercise. And next exercise is the extension of what we did now. Now we are asked to build an MPL model for the second stage stochastic Dakota problem. So now we did it for deterministic. Now let's go to the stochastic model because that's exactly why we use MPL in this course. And when we look at the formulation of the stochastic model in a solution, so we have some basic formulation where we explicitly specify all the values. We, as the researchers or as the modelers, know that it's a two-stage stochastic model. For any model in software or solvers, this model, it looks like some other linear programming model. So there is nothing special here. We have objective function, we have constraints, right? Many different constraints, but still these are the same constraints, which have right-hand side, which have decision variables with some indices, and we here for every decision variable there are 2 indices. For the here it's for product and for scenario. But from the point of solvers and MPL model in software, this is just LP model, and we could use all the constructs and syntax that we just looked at in MPL to add this model as it is here, just directly like that. Or here we have the compactor formulation of this model, which I will concentrate probably now because it's a bit easier, where we here also, so it's smaller one where instead of some of the parameters, we use letters to make it shorter and more concise. Again, we can take this model and the same as we did with sum notation, here we have sum notation, we can write down this model. And then as a result, we will get something which in a solution it will be called without stochastic syntax. So WO, it means without stochastic syntax. If you, so to open MPL files, we can close the previous one and we can open this one. And you see that here we use exactly the same syntax as before. We have indices, which are sets for scenario, products, resources, um, and we can model this two-stage stochastic model. But so you can check it in the solutions. It's nothing new. But what we really want to do, we want to to specify the deterministic model, which what we did before. Then we want to say MPL with a special syntax. All right, this and these parameters are stochastic. And then we want that MPL automatically builds for us this two-stage stochastic model so that we don't need to explicitly, for example, here, write down what is the objective function. It's the and that's the profit. It's the expected revenue minus total cost. Since we can just specify for MPL which parameters are stochastic, and then MPL will automatically build and solve for us two-stage optimization model. And that's what we will do now. I will base it on the deterministic model that we did so far, because the difference between deterministic and stochastic model is just some of the stochastic data. So I will use this version, some notation, or I will use what we did not from the solution, but right now. So here is deterministic model. I will copy this file. And here it will be stochastic. Now I open it. And let's see what we need to change here. So according to the exercise, basically, according to the stochastic Dakota model, we know that, so this is a contact formulation. We know that we just have three scenarios, and in every scenario, demand is stochastic. All right, that's why we have the demand constraints or bounds for every scenario, and then we have constraints for every scenario, and the objective function we optimize the expected value, and second stage constraints, they are this production, and not constraints but second stage decision variables, they are production decision variables. And that's what we want now to explain to MPL so that it automatically creates the stochastic two-stage stochastic model for us. So first of all, I modify the title. Now it will be called Dakota Model Stochastic. Now to generally explain MPL that now we are in the stochastic domain, I add one keyword. It's like empty section, which says stochastic, right? Then in every stochastic model, we have scenarios and we have some index for scenarios. Therefore, for that, I add section, which is called scenario, and it will be the set of scenarios. The set of scenarios I will call sen, even so I can call it in any way. And then in the same way as I defined other sets, because basically this is a simple set, I define here the set of scenarios. We have three scenarios, so it's 1, 2, 3, and semicolon. You see here I used words, but here I can use scenarios because I don't need to give some textual names to scenarios. They're just 1, 2, and 3. Then there could be problems where you have 20 scenarios. So for 20 scenarios, if I would define it the same way as I do now, I would have to write on 4, 5, 6, and so until 20, which is a little bit monkey job, let's say. So there is a shorter way to do it. And the shorter way is that when we want to define set or indices as some range from number, let's say 1 to number 20, we can use this construct. We write down 1, it's the starting number, then 2 dots, and then 20. And it means that here as the scenarios, we will have 20 scenarios, 1, 2, 3, etc. until 20. We have 3 scenarios, so I put here not 20 but 3. Then about the indices, nothing changes with this set. We still have desk, stable, chair, slumber, finishing, and so on. Now, we want also to define the probabilities of scenarios. Probabilities of scenarios is also the parameter, but since here we talk about stochastic modeling and we want explicitly say to MPL that this is the probability of the scenarios, we can add the section, and the section it's called probabilities. And now MPL, so to say, knows that this where the probability for this scenario is provided. And here we write down prob, because that's how I will call this parameter. For example, its syntax is the same as we used for price. Then, due to some reason, still probability is defined for every scenario, so I still should say that it's for every scenario. Even so, I guess MPL it would have understand that if it's probability section, then of course the index of every probability is this set from scenarios. But somehow, if I will not define it here, it will be an error. And then we have probabilities. And the probabilities are so 0.3, 0.4, 0.3. It's from the exercises in tutorial 3. They are provided these probabilities. Now, what else we have? So we have the data as it was before, but some of the data, some of the parameters are now random. And we also need to explicitly explain it to MPL. And we have a special section for it, which is called random data. So it's like data, but with another word, random. So random data. And our random data is demand. That's why before it was deterministic. Now it's stochastic. So I added from data and added to random data. And the demand is defined now for products, but also for scenarios. So now it will be, you see, it has 2 indices. That's why it's again the 2-dimensional data. And first index is product. So every row will be related to separate product, so to desk, table, and chair. And every column will be related to a scenario. So we start with the product desk, and it had the demand according to problem description as 50, 100, and 250. In scenario 1, 50, scenario 2, 150, scenario 3, 250. And now next, product, it's table, and it has demand 20, 110, and 203, 250 in 3 scenarios respectively. And then the last product, chair, demand was 200, 225, 500. So this is the random data. Then normal data, so deterministic data, nothing changes here, only random data changes. You could imagine that, for example, if cost, or not cost, but if price of products would also be stochastic. So if according to scenario 1, the price of product 1, so of desk would be not 60 but 70, we would also move this price parameter to the random data section, but we don't do it because prices are the same in every scenario. So what do we have here? We had before the variables, so we had only homogeneous variables, which are production and purchase. Now, when I go to this mathematical formulation of the model, and when I look at the objective function, I see here that we have x variables, which are purchase quantity of resource. You see that they don't have any kind of probabilities, they are not multiplied with probabilities, they don't influence any scenarios or by any scenario, so therefore they are stage 1 decision variables. And also there's two stage 1 decision variables because we make a decision about them before stochastic demand realizes, before the realization of stochastic demand. And we have alternatively or oppositely the stage 2 variables, and this every of these variables it has the index for scenarios, so it's how it differs from stage 1 variables. Stage 2 variables, they have the indices of scenarios because we produce variable y, we produce different amounts in different scenarios. We have two types of variables, that's why we need now to divide all our variables to stage 1 and stage 2 variables, and we need to explicitly explain MPL, whereas it's stage 1 and stage 2 variables. So first section where we write stage 1 variables, this is a section like variables, but we specify here which variables are stage 1, and this is the purchase variable x. Then stage 2 variables, so it's stage 2 variables, simple, similar syntax. It's production. So we used specific MPL syntax as stochastic, scenario, probabilities, stage 1, stage 2 variables to explain the objects not only of the simple LP model, but also specifically of this two-stage model. And we don't need to modify here anything more. So MPL, it will understand that when it calculates total revenue, since when for calculation of the total revenue we use production, and production is the stage 2 variable, it will understand that instead of calculating total revenue, it should calculate the expected total revenue and maximize every element of the sum, so or maximize every price multiplied by the production. Also, it will multiply it with the probability to find the expected value. The same it will know for the constraints, since constraints also has the production decision variables, which are scenario related. It will know that these constraints should be defined for every scenario, and we don't need to explicitly explain it to MPL. And if you compare it to the model without, to the model two-stage model formulation without usage of this MPL stochastic syntax, you will see that it's more tricky and more complicated. And here, if we want to just add one more scenario, we just can here simply write down 0.4. Of course, it's not that correct because total probability will be more than 1, but we can easily add probability and then slightly modify the data, and it will be the valid model. Now, after we did this, we can check the syntax. Again, the syntax is correct. And now we can solve this model. And the optimal solution is 1730. And it's the exactly optimal solution which you will get from the model formulated without the stochastic syntax, and that's the exactly solutions that we got from Excel solver, from that huge two-stage model formulation. Now we can have a look at the solution, and so here we should interpret this objective value as the expected profit for 3 scenarios, and then the solution is provided for every scenario separately. So you see that solution values for stochastic scenario 1, and you see here total revenue, total cost. Then for scenario 2, total revenue, total cost, and so on. We can see that total revenue from scenario to scenario is changing because according to the idea of two-stage model, we produce and sell different amount of products in every scenarios. But total cost, it will be always the same. Why? Because we decide about the purchasing amount of every product, not in scenarios, but before even this demand realizes, before the realization of demand. But of course, since revenue changes, the profit for every scenario is different. Yeah, so that's the solution, that the two-stage stochastic model formulation. And then the answer for the bullet point B of the exercise 1 in tutorial 4. And bullet point C, task in the bullet point C, it exists just to show you that there are many more functions, or there is more functionality of MPL that can be used to formulate the models. And sometimes this functionality is out of the standard mathematical modeling notation, so it can define more concepts. For example, here you are asked to assume that demand of products, so desks, tables, and chair, is can be described not with the scenarios but with some distribution. So scenarios are defined by the distribution. And for desks, its stochasticity is described as a uniform. So it's distributed according to the uniform distribution. For tables, according to the normal, and for chairs, demand is described according to the triangular distributions. And when we pick scenarios, we pick them from these distributions for every stochastic parameter. So let's modify our stochastic formulation to represent these stochastic distributions for every demand of the product. And we will do it in 2 steps. First, we since every demand for every product has different distributions, we first define the demand, and then we define the demand for all products. So what I mean by that, here as the random data, we have demand for all products and scenarios, but demand is different for every product. I will first define the demand for every product separately. So I do it by, I add one more section data. I can do it. So in my model definition, it's possible to have multiple data sections. They are read line by line from top to bottom. And here I will now, instead of one demand, I will define 3 demands. So first demand, let's say D, it's demand for desk. So this is a separate data vector. I want to say that it has the same as normal demand. It has the still index, but this index, it's not like over all products, it's defined for the specific product. So this index, it's equal to desk, because desks, this is demand day is defined for desks, and over scenarios, we have 3 scenarios, and the demand for the scenarios, demand for the scenarios of product desk should be picked from the uniform distribution. Uniform distribution, it's the concept from statistics, and this is a distribution. Here you have the probability density function, which means that the probability to pick the number from A to number B is uniform. You see here it's horizontal line, so it's the same. That's why it's called uniform distribution. So probability to have any number from this range from A to B, it's uniform. And to define this probability, we need to specify two parameters, A and parameter B. So to say that this distribution of demand T is uniform, I use the word uniform. And uniform, it's like a function. So here I specify this parameter A and B. It is 100 and 150. So it means that there is an equal probability to get the demand from 100 to 150. And demand lower than 100 is not possible. And demand larger than 150, the value of B, is also not possible. It has a probability 0. Probably it's not completely correct to say that it's not possible. It just has the probability 0. Right. In the same way, I will copy it. We define the demand, or in similar way, for table, which will be demand P, for the product table over all scenarios, but according to the problem description, it should be normal. So it's normal distribution, the most famous one. And for us, so this distribution, I guess you know how it looks like. From statistics, it's has the form of bell shape, so it looks like this. And this average or expected value, which is x value of this peak of this distribution, yes, it's first parameters that we need to know how to build this distribution, and second, it's how let's say wide this bell is, which is defined by the standard deviation. So these are two parameters that we provide to describe the distribution, and we would say that the average value for three parameters, it's for three scenarios, it will be 130, and that this standard, so that it deviates plus minus 20. It was for table and now for carpentry. So again, I just name it as demand C, carpentry. Sorry, not carpentry, but chair, of course. And then, so it was desk, table, we have demand for chair. And then here, we are asked to represent as a triangular distribution. And this specific distribution, as you might guess, it has the form of triangular. So it looks like this, where the mode, this peak value, it's defined by the parameter C, and the lowest value is defined by A, and highest value defined by B. So starting from A, from lowest value, probability increases until the mode, and then it decreases until B. And in our case, demand lower than A and higher than B, it has the probability of 0. So we need these three parameters, and let's say that lowest demand can be 20 for chairs, and that this mode value is 180. It's actually here on the second position, it's parameter B. So it's 180, and this mode, it's 120. Now we define the demand for every product, and now we need to specify, okay, what is then random data? What is the random demand? And here we want to concatenate the three vectors that we define. Some specific syntax in MPL, and to concatenate these vectors, we just use operator plus for this demand vector. So it's demand D plus demand T plus demand C. So we in this way, we, so to say, define the different distribution of the demand for every product. This is quite specific syntax, so you don't need to memorize it by heart, and you would probably, to specify something like that, you would first consult the manual, so the documentation, and all with that, write it down as it is here. And we don't need to change anything more, so we can now find the optimal solution. Of course, optimal solution is different to what we had before, because now we assume another kind of demand or another values which will be taken from uh, these distributions. And this was it for continuous Dakota problem. So we looked what kind of syntax we have to define the deterministic models. Not only Dakota, it can be used for anything. Then instead of explicitly specifying this two-stage model, so instead of using the same deterministic syntax for the two-stage stochastic Dakota problem, and instead of explicitly writing down that we want to find expected profit, we want to multiply probability with every uh, decision variable, or and so on. We just, in this bullet point B, use the stochastic syntax, which helps, so to say, MPL to understand what are our probabilities, scenarios, and then it builds this two-stage model by itself. And then we looked at some quite specific case just to see that MPL has many different uh, syntaxical structures, and we can define many things using it. And here we looked at the case when this demand for different products is described by one of three different distributions. And now we can go to the next problem, which is which will be mixed integer modeling problem. So this class of problems, it's quite popular. It's often also represented as a graph. But we will not concentrate on it. The most important thing here for us, or what we want to learn, it's so we want to have some model in practice, because we concentrated now on some production models. But here is one more example, a logistic model. And then we will have here some integer variables, and we want to see how we can define these integer variables in MPL. So the problem is quite classical. We have 6 cars. You see in this table, every row corresponds to the car. And these cars, they are supposed to deliver some pizza, not so important. So deliver some food or something, the order, to 5 customers. Each customer has one order, so we have 5 customers, and in this table they are represented as the columns. Delivery costs are given in the table. So you see that, for example, car 2, it to deliver for our company order 3 to the customer 3, it will cost 70 euro. Or it also can be the distance, that it's quite longer distance, and it will take much time for this car 2 to deliver orders 3. Then for some orders, delivery is not possible. So you see here some costs are not defined, because this car 1, for example, cannot deliver order 1. And then it's important that the last sentence here, the company wants to assign one car to each customer with minimal cost. So it's important that one car, it can deliver only one order. It cannot be such that car 2 delivers order 1 and delivers order 3. So one customer or one order corresponds to one car. And the idea, quite realistic aim of the company, it's all right, how can we assign cars to orders? That's why this problem is often called assignment problem, so that our total delivery costs are minimized. And here we have 2 subpoints, so 2 tasks. The first task is to understand this business description, and then formulate the model using some notation, so using the mathematical notation, what we did on the previous tutorials. And next one is to take the sum notation and implement it in MPL. Then we will be able to find the solution. And we start from the first point. And as in any modeling exercise or assignment, first we define the decision variables. So what exactly are we making decision here about? And what we decide is basically which car to assign to which order. More specifically, we decide, for example, for car 1, all right, does car 1 delivers order 2? Maybe no. Does car 1 delivers order 3? Let's say yes. Does car 1 delivers order 4? No, and so on. So we decide yes or no whether car delivers or not order for every pair of car and order. Of course, we have then some constraints which will say car cannot deliver more than one order, or order cannot deliver twice, or car 1 cannot deliver order 1. But this all will be specified in constraints. Now we just what we make decision about. So I will now start the formulation, and I will write down here that our decision variable, it's x. I will use x notation, letter I, j, and so the meaning of it, it will be 1 if car 1 or car I delivers order j, and it will be 0 otherwise if it doesn't deliver. Right, so if so for example, if car 2 delivers order 3, it means that decision variable, so x2 order 3, if it delivers this order, this car, it will be, this decision variable will be equal to 0. Will be equal, of course, to 1. Yes, and what I was thinking about, if it's not doesn't deliver, it will be 0. This decision variable, it's binary, as you can see, because it can have only 2 possible values, 1 or 0. It cannot be something in between. So 1.5, it's not possible. Car can deliver or cannot deliver the order. Now all the data, it's of course provided in the table, and what we can start with, so we can start the defining the model, and we start with the objective function. So objective function here, we want to minimize the costs. It says with minimal cost. So we want to make assignment, but we want to minimize the cost. And so question is, how can we mathematically specify this delivery costs, which we want to minimize? Let's start from the car 1. So for car 1, if we make decision to deliver only order 3 for this car, how the decision variables for this car will look like? I mean, decision variables x. So, of course, x1, since it's car 1, for order 1, it will be equal to 0. x1 for order 2, it will be 0. Then if we deliver order 3, it means that x1, 3 will be 1. x1, 4 will be 0. x1, 5 will be also 0. What will be our delivery costs regarding only this car 1? It will be 52, because that's the cost of delivering order 3 by car 1. So if we would deliver order 3 and order 4, our total cost would be for this car would be 52 plus 73. At the same time, decision variable x13 would be 1, but also decision variable x14 would be also 1. So I will write down the solution here instead of writing it down here. And so we see that to calculate the costs for one car, R1, we need to multiply every x or every decision variable of this car with the delivery costs of specific order. And of course, if we decide to deliver this order, like order 3, we will multiply, for example, costs 52 with 1. If we decide not to deliver the order, for example, order 2, we will multiply, in this case, 17 with 0, which will be 0. And then when the result of all this multiplication, we find the sum, and the sum is the total cost for the car. So if these are decision variables, x1, x for car 1, I multiply their values with the delivery cost. In this case, for the delivery of order 1 by car 1, we'll discuss it later. It's not possible, so here should be some coefficient. We'll decide what it should be later. But then for the second order, the cost is 17, then it's 52, 73, 72, and then we find its sum, and this is the delivery cost for car, of course, for car 1. And we decide where every x, whether it's 0 and 1, and when it's 1, it of course increases our delivery cost. Then for car 2, it will be exactly the same thing, except the coefficients. So for example, the delivery of first order by car 2, it costs 11, multiplied by the decision variable x, but now 2, because it's second car 1. Then we add here 39 multiplied by x 2, and so on, plus, again, here delivery is not possible, so it's something multiplied by x 5. Then we add here, we continue so on, and in every row we just change the coefficients and this first index, and then we will end up by the row for the car 6, which is 77 multiplied by x 1 plus this stuff x until 78 multiplied by x 5. And again, every x we decide, and this will be our total costs for all orders and for all cars. And now we could somehow write it shorter, of course. So first of all, this coefficient. Let's substitute these exact numbers with some letters. Let's add the parameter c, I, j, and this Cij has a meaning of delivery cost for car I of order j. The same indexes as for x, right? So here, again, this question mark we will decide later, but here instead of question mark will be C11. Instead of 17 will be C12, still first car second order. And then in the same way, C13, C14, C15. Now, we can see here that it's the sum for this car 1, where we multiply costs of delivery for car 1 with the decision variable, so whether we deliver or not this order. And we again can shorten it to the sum. So for car 1, we can use sum notation to write it down shorter, and we can write it down as, for the car 1, of course, as sum over C1 J multiplied by X1 J1, again because it's the first car. And for J, these are orders from 1 to 5, because we have 5 orders. This is for the car 1, which corresponds to this row in objective function. Then for car 2, everything will be exactly the same. So cost for car 2 will be, again, sum for all orders. But now we multiply C2 J X2 J, because it's the second car. We will do the same stuff until the last car. So plus sum J equals to 1 until 5. And then for car 6, for over J's, X6 over J's. So we see that we get here again the sum, but now every element of the sum, it's not some multiplication. It's the sum of the sums. So we can write it down shorter as this sum. And what is changing between these all sums? It's only this index. And this index is corresponding to the cars, of course. So we find the sum over all cars to find the total costs. We have 6 cars. You see it here. And we find the sum for these 6 cars. And every element of this sum are the car delivery costs. So this J1, car delivery cost for all the orders. C I J X I J, like this. And these are total costs, which we want to minimize, of course. So I will copy this, what we calculated. So we want to minimize it. And now our constraints. So subject to, what are the constraints? So according to the problem, so one car can deliver at most one order. Since we have 6 cars and 5 orders, one car will definitely be like without work. And then we also know that every order should be delivered. And we start with that. We will start from the constraints that will force every order to be delivered, because in the objective function we don't force it anyhow. Theoretically, in the objective function, if we, for example, look at the objective for car 1, we could say that car 1 should deliver order 2 and order 4. But we know that it's not possible, and we need somehow to add constraint to say this. And if we look at the orders are rows. So what is possible? So solution like this, it is valid, because order 2 is delivered by car 1. It's correct. Solution like this, it's wrong, because it means that car 1 and car 4 delivers order 2. And also a solution like this, it's of course not allowed, because it means that order 2 is delivered by none of the cars. So in other words, we want to say the sum of decision variables for this column, so for order 2, for all the cars which deliver or not deliver this order, but the sum of all the decision variables should be strictly 1, should be delivered by one and only one car. So we write it down as the sum, but now we talk about orders, so the sum should be for all cars. So I, starting from 1, ending with car 6, for x, ij, and if we talk about, let's first look at the order 1, so for all order 2. So for order 2, it would look like this, should be 1. And it's basically say that this column should be, the sum of decision variables for this column should be exactly 1. Now we want to, this constraint should be true not only for J2, not only for order 2, but for all orders. So it's J, and here for all J's in the range from 1 to 5. Because we have 5 orders. We specify this. Now, we want second constraint, as I said, what we want to define is that every car can deliver 1 order or 0 orders. So some cars might not be used. So again, using the same logic, we define the sum, but now it's the sum for rows. And we say that for every car, let's first look at the car 1, so x1, for all the orders, so over all orders that we have, and we have 5 orders, the sum should be at most 1. So car 1 should be not used or used 1 time to deliver 1 order. And here, of course, J. But it should be like that, not for only car 1, but for all cars. So for all I in start in the set or in the range of all cars that we have. These were 2 constraints. Now, what else is missing is, so variable x, it's a binary, right? So we can simply write down that it's binary. Like this. And basically that's it. It's the problem definition. So in the objective function, we minimize the total costs, which is the double sum over all products and over all cars. In constraints, we specify that every order should be delivered by 1 car, and we specify that every car can deliver at most 1 order, not to deliver orders at all. Now, let's go back to this question mark. So we had a question mark for cases when a delivery is not possible, and we avoided it because now we substituted this exact values with Cij. But what should we put as a value of Cij, for example, C11? So there are 2 approaches how model this situation. First of all, we can explicitly add constraints, which will say that this delivery is not possible, that it will be always 0. This car 1, for example, will never deliver order 1. And we can add it using the constraints, of course. So we say that x11 is equal to 0. And then when we write it down explicitly in this way, it's clear that car 1 will never deliver order 1 because we made it explicit. Another approach, it's so when we will put this model to some software, this software, it will try to find the combination of deliveries so that our costs are minimized. Therefore, most probably, this sum of the costs that are relatively high, like 78, for example, car 5 delivers order 3. Most probably, it will be avoided by the optimization software because it will be too expensive. So to avoid such cases which are not possible, the trick can be that instead of this minus sign or whatever, we would put here, we would assign some costs which are very high, like 1,000. In this context, it's quite high cost. It's like big M. And then this big M, it's such huge that it will guarantee that our optimizer will never choose this delivery as a part of the optimal solution because it's not worth it. So these are two types. And now what we're asked to do, so we modeled it. Now we're asked to define this model in MPL using its syntax. For that, let's go now to MPL, of course, create a new file. And then we start with the title section. And let's call this problem delivery service, semicolon. Then we go to indices, so the sets that we have. And we have in this problem two sets. These are what is normally index I, these are orders, and the cars. And we have 6 cars and 5 orders. So let's write down it like that. Cars, we have 6 of them, and orders, 5 of them. Now you see that if we would have 10 cars, the only what would change here is this second number in this construction. So it would be 10 here. If we would have 20, it would be 20. So we can make it a little bit more abstract. And we can add here the data section and explicitly specify in this section how many cars do we have. So it would be a number of cars. And we have, of course, 6 cars and number of orders. We have 5 orders. And then instead of, we can take this number of cars and number of orders and put to the index definition. The next what we have is, of course, the data. So, and it's another section of data. We can have multiple sections with the same name, so data and data section. And here, what data do we have? We have this Cij, which is defined with 2 indices for cars and for orders. So we'll call this cost. It has 2 indices, cars and orders. And this is a multidimensional data vector, it's matrix. And here every imaginary row will be related to cars and every column to orders. So it's exactly as in the model description. In rows we have cars, orders are in columns. I could print it manually, but I will just copy the solution that I have already, or I have done it before. So this is the data. Here as the big M to to avoid the delivery of not possible combinations, we use 100. I experimented, it's sufficient to use here even 100. So this is the data. And the next element that we need to define, it's of course the variables. Here we have only one variable, which is x. And this variable, it's special in a way that it's a binary. So there are 2 ways to define binary variables. We can specify in the bounds section that variable is binary, but we can also just write binary and then variables. So if this variable would be continuant, continuant, we would use only word variables, but now we use binary variables, binary, and we write down here, so it's whether car delivers order. I won't use here some human words. I will just use this X, and it's defined for cars and orders. It has two indices. Whether car delivers some order. Then we have, if we have now decision variables, our objective function is the minimization function of the costs. So where it is? Yes, it's here. And we see that it's a double sum over all cars and over all orders. You should also understand that it doesn't matter so much what comes first, over sum over all orders and then over all cars, or vice versa. And elements are costs and this decision variable X. So we will write it down exactly like that. It's minimization. Then we could use here macro, but since we have only one element, cost of the decision objective function, we don't use macros so much. What I will do, I will provide a name for this function. So expense equals, and then we have this double sum over all orders and cars. So I don't need to write something like sum and then sum again. It's enough if I write down sum and then orders. And if it would be only for orders, I would put here the column, but I put here cars. So it's over orders and over cars. And then I write down cost multiplied by X as the element of this sum. And then MPL will know which indexes they have and how to find this objective. And now constraints, subject to. So first constraint, it's for every order that the sum over decision variables related to this order over all cars should be 1. I will call this order delivered because it says that every order should be delivered. It is defined for every order, so this constraint has indexes of orders, and it is the sum over all cars of decision variables X, and it should be exactly 1. Now for the cars, it's almost the same. I will call it car usage, but it says that this constraint is defined per car for every car, and the sum over all orders of deliveries for this car should be less or equal to 1. It cannot be more than 1, but it can be 0. And then we are done. So here are only new concept or two new concepts. We have binary variables and we have double sum. It could be also triple sum over orders, cars, and let's say some periods or months. So you can add here as many dimensions as you want. And now let's check the syntax of this problem. Okay, it wants to save delivery service. Syntax is correct. Let's solve it. So our total costs are 152. That's the minimal cost that we get when we deliver all the orders. And let's go to the detailed solution. So again, the total costs are here. Now let's see. So you see that variable X, it corresponds, we have many of these variables for all the combinations of cars and orders. And for example, car 1 for order 1, it has 0, it has activity 0, so it doesn't deliver order 1. And it's great because that's what we wanted, because it cannot deliver this order. It was prohibited. But what this car is delivering, it's delivering car 1 delivering order 2 because it has value 1. And then this car, naturally, what we specified in the constraints, it doesn't deliver any other orders. So for car 1 delivers order 2 for normal people, to say, explain like for people but not for machines. Then car 2 delivers order 1. 3 delivers order 5. 4 also delivers the order. And car 5, it has all the values 0, so it's this car which we don't use. And it's natural because we have 5 orders and 6 cars. And that's why it was important in this constraint for the cars to say that car can be used or can be used once or not at all, but not more. If we would put here equal, we would get infeasible problem because it wouldn't be possible to assign all the cars to the orders. Let's try to do it. What will happen? So if in this constraint I put 1 equals 1, it means that I say that every car should be assigned to some order. But every order shouldn't be delivered more than once. If I try to solve, it says integer infeasible solution. So problem, it's not possible to do it. And it's logical, makes sense. So this was the mathematical and MPL model for this problem. And now there is the last small phrase, which says load data from the external DAT files, DAT with extension DAT. So what that mean? It means that if you look at this model, what data do we have here really? It's data about the delivery costs and the data about the number of the cars. These are and orders. So these are 3 things that we might change. So if we have some other day when costs increase or we have more cars or more orders, that's only 3 items which are changed. As long as there are no any strategical or so conceptual changes in this problem. And therefore, it's always or often convenient to define the model in one place in this file and to load the data itself, like the specific values, from other place, so from database or from other files. And yes, I would now show the distinction, the example how we can make a distinction between this model definition and model data. And so we are asked now to, instead of hard coding this data in this MPL file, we are asked to read this data from external file. But we can also read it from database and even from Excel worksheet. Let's first read it from external file. And for that, I need to create these files, which will include this data. So I create a new file. And this all are files with data. These are textual files. So you can create the txt file, which I will create now. I will call this txt file. You can call it any way, but in any way, but I will call it delivery n because it's indexes. And then I will, for myself, for understanding, provide this file, the extension det. But still, it's if we change the extension of the file, it's still the txt file. Now I open it. So if you don't know how to open other files on Windows, you just choose with right button, click on it, then open with, and then you choose with which software you want to open it. So I open it with some text editor, can be any. And here I write down the data, and which data I want to put here. It's this 6 and this 5. So I just simply put here 6 and this 5. And how this works? It works in a way that MPL, and it's located on my desktop, and this file, which data file which I create, also located in the same folder on the desktop. So I want MPL to read 6 and 5, not from here, but from external file. So I write it down. Here is how I write it down. So I write down the like this. Like this. So I write down the data file, which means read this data from data file, and then the address or path to the file. The easiest case it's when your MPL file and data file are in the same folder, as in my case they're on desktop, but it can be any other folder. Then you specify here only the file name, and this file it's called delivery and .dat, DAT with extension dat. So I specify it 2 times, and what MPL really does, it goes to this part of the code and it says, okay, I need to read something from this file. It opens this file and reads the value. So it reads this, it knows that it should read one value, it reads the value 6, and then it goes to the next line and it sees it also needs to read data from the file, and it reads them the next line. So it reads the next line in the file, which is 5. And with this contents of the dat file, I can read at least these 2 scalar values from another file. Let's test it. So you see it works. It provides me exactly the same answer, even so I put exact values to external file. Now in that files we can write comments, and comment we write with the exclamation mark. Yes, so we add comments with exclamation mark, and we can write here, for example, number of cars. So we know that this means number of cars, and this means number of orders. Also, so this comment, they will be not read by MPL, and also it skips the empty lines. So in this way, I can specify that where are what is number of cars, what is number of orders. And then when we look, we have also here data, which we can also put into external file. So I can copy this statement here. So now there is small technical thing that if you see we exit this data section, so it means that when MPL will come up to this line, it will start reading data again from the very beginning. So I would like now to add all this data to the same file somewhere here. But since it's in another data section, it will again start reading this file from the very beginning, and it will be an error. And to solve this limitation, I should either put this line in the same section, so here, but I cannot do it because my cars and orders indices, they are defined afterwards, and it should be in the correct order. Or I can just use another file. So I will create another file. I will call it delivery cost. And again, I create a new text file. Let's call it DAT. And in this file, I put the exact data which I had before in the model definition itself. So I put this, I had this in the model definition without the brackets, and now it's defined externally. This. All right. And if I did everything correct, when I again solve the model, I see that my optimal solution and solution didn't change. Now, it means that if I want to make some modifications to this model, for example, I find out that delivery costs for car 1 and order 2, they are not 17, but they are 20 due to some reason. I can modify this data here in this DAT file, DAT file, and in the model itself, I don't change anything. I press the button, and you see I will get a higher or another optimal solution, of course, because my costs are higher, or probably I get another solution if this price changes everything. And this is quite handy if you, for example, you are the modeler, you develop the model, and other people, they have no idea how this optimization works. They just want to use this model for their specific data. Or if, for example, you want to connect your model definition to the ERP system and work with the data from that enterprise ERP system so that you don't need to modify with hands or this file. And then instead of using a textual DAT file, you can do almost the same thing with the database. And this what we have here, it's called model definition. This what we have in these files, it's called model data. And model definition plus model data, it's called model instance. So we can have many instances with one model definition if we just somehow modify the data that is used in these instances. And this was it with the exercise 2, in which we modeled quite an interesting case of assignment problem. So it's a classical assignment problem. Then we looked how can we define this cost of pairs of car and order which cannot exist. And we then transformed mathematical formulation into MPL, and we modified it again so that all the data is located in the external files. And that's what it for today. So thank you for attention and have a nice week.